Hello, guys. So we have Jaspreet Oberoi with us. He is an ex Thaparian. He has been he has been a part of One Qubit from past few years. He is the director at One Qubit and heads the ML department there. Uh, Jaspreet, how are you doing?
I'm doing good. Thank you. Thanks for giving me an opportunity to talk to you guys. I'm really excited about it.
It's a really pleasure for us as well to have you. Can you introduce yourself quickly so that our audience knows who we are having a session with?
Yeah, of course. So my name is Jaspreet Oberoi. I was part of Thapar from 2004 to 2008. I completed my BE engineering, electronics and communication back
Okay.
then. So I don't know whether it's the same right now, whether we still call it B-Eng or not.
Yeah.
After that, I got a campus placement at Futures First.
Okay.
Maybe they still come to the campus. And around working for a year or so, I came back to my town. Gurgaon didn't feel like home to me. I started my own coaching institute for basically coaching students of 11th and 12th grade.
Okay.
Um, and then slowly I realized that I need to maybe get some more training in the discipline I wanted. So I applied for various universities in Canada.
Okay.
And the first one I got, I took it and I moved. So I was in the Masters of Science program at Simon Fraser University in Vancouver.
Okay.
Um, that the focus was again, it was electrical and electronics engineering. That's what they call it here. There's no electronics and communication as such.
Okay.
But then I could choose my courses, and I made my degree to be a combination of electrical and computing science.
Okay.
And I specialized in optimization, machine learning, and big data.
Okay.
During my master's, I got an opportunity to do an internship at
Mm-hmm.
One Qubit
Mm-hmm.
back in 2013. The reason I chose it was something unique. One Qubit, if you already don't know, is the first software company of the world to work with quantum computers. So
Okay.
that's
That's really
what
cool.
attracted me, and I
Yeah.
took that position as
Okay.
an intern. It was a startup back then, and I was the fourth person to join the company. And
Okay.
currently, it's around 130 people. So I've
Okay.
basically seen that company grow from one room to couple of rooms to now quite a big establishment.
Okay.
And as you mentioned in the introduction, I started as a research intern. Then I went on to, of course, become a full-time employee as a research scientist. Then I started leading the machine learning team, then heading the machine learning division. And last year, I got promoted to be the director of the machine learning and the optimization division. So around half of the company that is One Qubit right now. So yeah, that's a long way to answer your question about introduction.
Yeah. Okay. So the journey is really exciting, uh, from Thapar to Canada to One Qubit. Yeah. So we'll discuss with your early life at Thapar. Like, what were your interests? How was your life
Yeah,
at Thapar? Did you enjoy engineering?
yeah,
How did you get started with the quantum computing? So, yeah,
yeah,
if you can tell us something about that.
yeah. Of course. Um, so my love for engineering is basically due to my love for math and physics. So those are
Okay.
the two subjects that I really
Okay.
really liked. Starting from I would say grade 8, 9. Math, of course, from the very beginning, but starting grade 9 or so, I loved physics.
Okay.
So my dad's a doctor. So as back in India, it's almost a given that if your parents are doctors, you would do the same. So of course, I was
Yeah.
given kind of a direction from my parents that I'll be a doctor. But then I had to revolt, I would say, in grade 10 that no, I don't like biology that much. So please
Okay.
let me go into take up the non-medical courses in grade 11. So
Mhm.
my parents, they kind of told me, of course it's fine, we won't force you, but
Yeah.
then do well and at least get an admission in either um, one of the IITs or just at home, because I belong to Patiala,
Yeah.
in the Thapar University. So I got a rank of I think 3671 was my rank in IITs. So
Okay.
I could get into IIT, but I couldn't get the discipline that I wanted to.
Okay.
Um, I actually wanted to go into mechanical, but I couldn't get that with the 3671 rank.
Okay.
So the AIEEE rank was pretty good. Um, I think it was 37 in Punjab, so I got into Thapar. And the choice I had was electronics or computer engineering. Um,
Okay.
if I go back in time, I would have chosen computer. But back then, the thing was electronics is the top one, so just choose that one. So I'll be very honest with you. I did not have any love for electronics just because it was supposed to be the top one and my rank was good. I chose it.
Mm-hmm.
Um, while in Thapar, I really loved everything that happened from from the friends I made, from the environment that the university provided, from the
Mm-hmm.
subjects that I got a chance to study. Everything was really good. I had friends both day scholars and in the hostel, so I kind of enjoyed both lives. I used to stay in the hostel as well.
Okay.
Really loved the lunches, the
Okay.
the rajma chawal and kadi chawal. Everything was really good.
Yeah. Yeah.
Um, and then I think around the third year when we had to choose where do we do our internship, that's when we actually got serious, or I got
Mm-hmm.
serious about thinking about there's a life beyond Thapar. And
Okay.
so I chose Arisent. I don't know whether that company exists right now or not. It
Mm-hmm.
it it has something to do with Flextronics and other companies of in that time. I
Okay.
chose Arisent. I went there. I lived in Gurgaon for 6 months. Um, Completed my internship. It wasn't something I really loved. It was all pure coding in Visual Basics, and I was automating something that they used to do manually. I did it pretty nicely, and the
Okay.
project was a success, and I got an A plus and everything. But I didn't like what I did there, so that gave me that gave me an awakening that probably I need to do something else in the rest of 1.5 years so that I don't get into this kind of a job. So
Yeah.
I started thinking about business more. I started thinking about MBA and things around it.
Yeah.
So, of course, again, something that a lot of engineers back in India do. I spent, I think, all of my fourth year in preparing for the CAT exam.
Okay.
Um, nothing of the sorts that I stopped thinking about engineering or that I stopped enjoying. I think the enjoyment that Thapar provided continued. We had good times both in terms of extracurricular activities, but also trying to learn more from the courses. I still remember there were certain courses that I really loved, microcontrollers being one,
Okay.
um, analog circuits
Yeah.
being the other one, VHDL being one. So things that were really interesting,
Okay.
where we could basically build something. One
Yeah.
of my project was building a traffic light controller and something around it.
Yeah. We still have that.
Um, nice, nice.
Yeah.
Um, so yeah, so Cat. So during my internship and later, I took coaching. I sat for the CAD exam. Again, just like IITs, it wasn't good enough to get into an IIM. I could get into something below IIM. I think my percentile was 98 something, not good enough. So I didn't get into an IIM. So I dropped the idea. I didn't go to any other B school.
Okay.
Um, Futures First gave me an opportunity to take up a job where I won't be coding, but I'll be basically in a job which is trading. So
Okay.
I'll be using my analytical skills and things that are not necessarily engineering specific. So I did I did that. I chose that over the other two job offers that I had, which were purely um, software engineering.
Okay.
So I had basically three placements. I chose that one. It gave me good exposure about life, how how things are when you actually move out of your place, how things are when you're earning
Yeah.
yourself, and how things are when you look at the business side of
Yeah.
the world. I made good money, but there was something missing, as I said in my introduction. And
Yeah.
after about a year, I resigned from that job and I came back home.
Okay.
Um, so yeah, that is the first part of the story. When I went to SFU, I realized that engineering in the Western world is a bit different from engineering in India, and
Okay.
not that it's bad or worse in India. It's just that in India we put a bit of more stress on what exists in the books
Yeah. Yeah. Yeah.
rather than what new can we do and what
Exactly.
extra can we do. So just the concept of, can you come up with an idea and work on it and publish a paper, versus can you make sure that you understand this book and answer the exercise questions that exist in that book.
Yeah.
So this is what I realized when I came here, and that kind of gave me enough interest to start thinking about engineering again and
Mm-hmm.
moving away from the business and the finance side that I got into.
Mm-hmm.
So I started with classical computing, nothing quantum. My supervisor was solving certain problems for
Okay.
communication systems, and we wanted to do it better than what the current technology provided back then. So I wrote two papers with him, and while I was still in my master's, I started looking for an internship so that I could make some money, because the I was basically on some kind of scholarship, so I wanted to make more money.
Yeah.
And this is when quantum computing came into picture.
Okay.
I had no experience in quantum computing. Um, while I applied for that position, I took Coursera courses to understand and learn about it
Okay.
before my interview. So that's what I did. Because it was a startup, because quantum computing still is new, but back then
Yeah.
was
Yeah.
brand new. They didn't expect anybody to be a master. They just wanted to see whether I am interested enough and probably capable enough. So that's how I got my position.
Yeah.
I remember the CEO talking to me. That interview was in a pub, and
Okay.
we had a burger, we had a beer, and we went home. And I had to email him 2 weeks later that I didn't need an answer, and he told me, "Sorry, I thought I had already told you that you're in." So that's how I
Okay.
remember my first interview in Canada, and
Yeah.
and luckily I haven't had to take part in another interview. So that was my first and the last till now. After that, it's
Okay.
been building the team, managing the team, so taking a lot of interviews rather than giving. But of
Okay.
course, I've learned a lot. Mhm.
So your journey for the Thapar was really exciting, I guess. Starting from an electronic engineer and landing up a job at 1 qubit. That's really amazing. Uh, and that too without any prior knowledge of quantum computing. Uh, so yeah, that's
Yeah,
really exciting.
yeah.
Uh, okay, so
Yeah, it's important to mention this because I think there is maybe a myth or a misnomer that when somebody sits in an interview, the only thing
mhm,
that that person should know is what the company that they're sitting the interview for does and what are
yeah,
they interested in. I think in an interview, it goes way beyond what the
yeah, yeah,
subject matter is. I think one needs to think about interviews in a different manner. And I'm sure my view about the interviews like they happen in Thapar is too old. I'm pretty sure things must have evolved, and I'm pretty
okay,
sure people, especially in Thapar, being one of the premier institutes, probably provides insight and
yeah,
kind of training to its students. But I'm just saying that it's good to keep that in mind, that it's not always about knowing your and or gates or your C++. It goes beyond that.
yeah, exactly, exactly. That's what we focus in the DSC as well. So we are very much into building projects, as we think that projects are the real core knowledge which one should have before going
Yeah,
through the books. And it's not just the books which will give you all the knowledge. So,
yeah, yeah,
moving forward, I like to know that how to build interest in quantum computing. Like there is so less stuff out there on the internet. There are very less resources to learn quantum computing and actually understand what quantum computing is, because quantum is a very heavy word. We use it in
yeah,
physics, and actually it is something which by default you can't understand. So how did
yeah.
this thing came to you? Like, how did you manage to learn quantum computing and start a career in it?
Yeah.
And also the fact that, sorry to interrupt, also the fact that, like right now we are facing scarcity of resources for quantum computing, but at your time, at the time when you were learning, it must have been really tough to get into this field. Uh,
Yes.
so some more insight into it.
Yeah, you're right. And that's a very good question. And I get this question a lot in general. So I won't be able to even give you today one link to a course which I would say, please go ahead, complete this course, and you would know what quantum computing is.
Exactly.
So that's not possible. Um, Sad part or fortunate part, I think it's both. Sad because I think there's a lot of interest, and I think the field can benefit from more and more people getting interested in it. So there should be enough resources that get people interested and give them at least the basic knowledge, so that they can make a conscious choice of going for it or not.
Yeah.
And fortunate because it doesn't have as much resources available, and because the research hasn't been completed yet, this actually invokes interest in people to do something new and to do something novel and to
Exactly.
contribute to this field. So if you are somebody who likes math, if you are somebody who likes physics, if you're somebody who's good at algebra, if you're somebody who understands matrix operations well,
Hmm.
if you're somebody who likes equations,
Yeah.
this is the recipe for you being a good quantum researcher. In the end, it's all algebra. In the end, it's all complex numbers.
Okay.
And the play of these things together bring about what basically quantum computation is.
Okay.
Going beyond it, there's of course a philosophical aspect to it as well. And the philosophical aspect is that the resources we have today, the way mankind has thought about computation till now, and that is our transistors and how we are trying to scale transistors to make more and more powerful devices.
Yeah.
Maybe that's not the only way to exceed or
Yeah.
succeed in the world of computation. Maybe there is a way to actually exploit physical phenomena to actually do some work for you. For example, if somebody tells you that you need to transport 50 gallons of water from point A to B, one way to do that is get a tanker, fill that tanker with the water, drive it, and take it to point B. Another way to look at it is maybe first we should check whether there's actually a slope from A to B. And if there is a slope, then we can use gravity to transport the same water without putting too many resources into it. So this is a good analogy to understand quantum computing, that if you are able to map your problem or to mold your problem in a way that it can actually exploit physical phenomena, that is the entanglement, the tunneling, and other things that exist in quantum computing, then probably that's a better way to solve that problem rather than putting CPUs and GPUs to it. So there's the math of it, there's the physics of it, but then there's also the philosophy of it, that do we need or can we actually take a step back and try to look into a new paradigm of computing. So that together played a big part in making me interested in it. And as one of you asked the question, without so many resources, how did I do it? I was lucky. Let's be very honest. If one qubit has to hire today, we won't hire a person that had limited knowledge that I had back then, because the times have changed. Even our expectations have changed. So we want somebody a bit more informed than what I was back then. But that also means there are more resources available now. So that person should be able to look into the courses that MIT, Harvard, and others have already designed and created and put online. So rather than depending on just blogs and other internet resources, I would always recommend go for the Coursera and the, what's the other one? I think it's
EDX?
Academy or something. So yes, EDX. So these kind of platforms have good courses from some reputed quantum professors, quantum physicists. So that is always the first step.
Okay, so that was exciting. So you mentioned that one qubit does not now take somebody who has limited knowledge about quantum computing. So can you explain if someone wants to join one qubit? So how is he gonna follow the path? Which path he's gonna go so that he lands up a proper career in quantum computing, not just the one qubit, but proper quantum computing.
Yeah. So yeah, I think now there are 6 to 7 well-known teams, and by teams I mean institutions and companies that do work in this space. So now one qubit is not the only one. Back in the time, we were the only one. But if somebody wants to make a career in quantum computing, I would say that they need to have a strong background in physics and math. Engineering is good, and then probably a master's that has physics and math as a major, and probably few courses under their belt, because at least in the Western world now, almost all the universities have quantum computing courses. So for example, the SFU, the university I did my master's from, back in the time did not have it. They have it. UBC has it. University of Toronto has it. The partner so that would be interesting for students at Thapar University to know that if they are interested in quantum computing, they should look into the opportunity of, I don't know whether that program is still on, but back in the time there was a student exchange program between Waterloo and Thapar. So that's a good opportunity to come here for a semester or two, take a couple of courses, because the Waterloo program is very, very strong. And then basically go about it that way. And I think platforms like yours and other similar things in the IITs and other premier institutes should start talking about this in India as well.
Yeah.
If I am not wrong, I did hear the news last year of Indian government putting in a substantial amount of money in quantum computing, and I think part of it was to be given to the government institutes to start these programs.
Yeah.
And if it has not already happened, it would. But I think the best way would be for somebody to now actually learn about it in an institutional setting,
Yeah.
because back in the time it wasn't available, but right now it should be. And if
Okay.
not, then they'll have to move out of India to do so.
Okay. Okay. Next question is related to quantum computing's quantum computing being applicable in various fields. Like, what are the fields
Mhm.
where quantum computing can actually solve problems? Like, where it is used?
Yeah, yeah. Good question, because it's not obvious for many, and unfortunately, the internet articles that one finds when one Googles, they are
Yeah.
a bit misleading on it. Um, so even from a very reputed journals, and by journals I mean media outlets, not scientific journals, like the Wall Street or the New York Times, or
Yeah.
even the Economist, they've covered quantum computing pretty well. But one thing that they've been unable to do is set few things right, and mainly because of the media hype around it. So
Yeah.
as quantum computing stands today, um, today it cannot solve a problem better or faster than the classical computers that exist today.
Okay.
And the main reason for it is the hardware, um, the hardware advancement on the quantum computing, it has only picked up in the last 10 or 12 years.
Hmm.
Um, so what that means is the quantum computers of today are good, but they are small.
Okay.
Small in terms of the number of bits that they have, which basically dictates the amount of information that they can process.
Okay.
So because of the smaller size, currently we can only solve small sized problems,
Like,
which anyways
how small it
classical
is if
computers can
you
do well.
compare it? How small
Yeah,
it is if you
yeah,
compare it to a classical computer?
yeah. So the best ones are right now from Google. Um, Google's it is around 52 qubits. What that would mean is if you have a problem that has 52 variables, awesome,
Okay.
we can do it.
Okay.
If you have problem which is bigger, we cannot.
Okay.
And and 52 variables is very, very small.
Okay.
It's
Yeah.
basically if you look at a machine learning problem, and what you want to do is, let's say you want to differentiate between images.
Yeah.
An image normally, even if taken from a low resolution camera, would be, let's say, 1000 by 1000 pixel, 1024 by 1024, or smaller ones can be at least 50 to 50 pixels or 100 to 100 pixels. So that comes out to be a 1000 variable or a 2500 variable problem.
Yeah. Yeah. Yeah.
So that's the restrictive part.
Okay.
Um, and the problem in hardware is that quantum hardware is of course sensitive. It is not
Yeah.
as robust as our classical hardwares are. So you can manufacture a classical computing chip today, and
Okay.
without putting in much of effort, you can put it in a computer and run it. Quantum hardware, on the other hand, is very, very sensitive to all the external um, perturbations. So be it the external magnetic field, be it the external electric fields, the light, everything, it actually affects, because of the way quantum phenomena works. It is at a very, very smaller and minute scale. So
Okay.
that's why it's pretty sensitive. So
Okay.
the whole effort of these big players like the IBM, the Googles, and
Yeah.
the Microsofts, now even Amazon, is to either make their own or to fund smaller startups that are making these hardwares.
Okay.
So that is the background of it. But as far as the kind of problems that quantum computing can address,
Yeah.
of course, a universal quantum gate model computer would be able to address everything possible,
Okay.
but it wouldn't make sense to make it address everything possible.
Yeah.
It would make sense to only target the problems that are harder for classical computers today to be able to be solved by the quantum computers, because of course they are expensive and running them would be expensive. Until the technology becomes mainstream, um, these computers would always be in the range of millions of dollars.
Yeah.
Um, so machine learning being one, solving hard optimization problems being the other, which basically translates to every important industry vertical that you can think of.
Okay.
But a very, very interesting use case is, of course, encryption.
Okay.
Um, our whole intranet and everything is based on a particular encryption model
Yeah.
that assumes that because that problem is harder to solve for classical computers,
Yeah.
nobody would be able to break the encryption.
Yeah.
But if we get a million qubit sized quantum computer,
Okay.
which of course is far, far away,
Yeah.
but considering that we have millions and millions of bits in a classical computer, it is of course possible that eventually we would have a quantum computer with million qubits,
Yeah.
that encryption would fail.
Yeah.
And thus it is one of the important areas where everybody is focused on, including the governments of course, all the countries.
Yeah. Okay. So I guess that was really exciting applications of quantum computing. As you told, crypto is a field where we can actually apply quantum because, as you said, the
Yeah,
notions of crypto are based that will not be able to solve the or crack the code with the classical computer, or it'll take millions of years. Okay.
yeah,
So, as you
yeah,
told that quantum computers are housed in like big firms like Google and Amazon and Microsoft. So how is it gonna be available to developers and common Commonwealth? So how is that gonna happen?
yeah,
Are they gonna be
yeah,
available like desktops, or they are gonna be available like a software as a service or a platform as a service?
yeah. Again, a very good question. I don't want to be, though I'm not a famous personality, but I don't still want to be on the wrong side of history. So I won't say things today like some people said a few decades ago, that nobody would ever need a desktop at home.
Yeah.
And this is a famous quote back in 1960s, 70s. And now we know even within one household, we have, if not more, at least 10 different kinds of computers, be it your phones,
Yeah.
other handheld devices. Um, but with my limited understanding and some years of experience, at least in the near future,
Yeah.
I don't see a wide prevalence of quantum computers,
Okay.
at least at the household level. I do expect that bigger universities should have at least one, and probably would have at least one.
Okay.
But um, having been in this industry for long now, I can totally see that the model that this quantum computing industry is moving to is providing access to these computational resources through cloud.
Okay.
Just like you don't need to buy clusters of CPUs and GPUs today,
Yeah.
and you can train your algorithms and solve harder problems using Amazon, um, Azure, and GPC instances. In a similar fashion, you would be able to access the quantum resources through the same cloud. So,
Yeah.
for example, um, we are currently working with Microsoft, and by we I mean 1QBit, to roll out their quantum Azure services. So just like everybody uses Azure for classical computing, they would be able to make an account and use quantum resources. So we are the software partner for Microsoft in that, and they have a couple of other hardware partners. So probably later this year, you'll be able to go in, create an Azure instance, and basically access cloud through cloud actual quantum resources. Whether this would stay to be the model, whether it would change to more and more availability of quantum, we can't look into the crystal ball to say that, but at least in near future, I see it through cloud computing and not through a big availability of such chips, at least at the household level.
Yeah. So that means we'll have access to the cloud computing in some way. Like, is it rather a platform, or if not the chipsets? So now, if
Yeah.
once we have the platform, how are we gonna develop something on it? Like, is there something different language for it because it's different from classical computer? Are our old school languages gonna work on it, or is there something else? Are the concepts
Yeah.
same?
And also, yeah, also like if developers have access to these computers, so in what ways do you think we could make use of these resources? And some examples, if you could give.
Yeah. Yeah. So one of the thing that 1QBit does is actually make low-level compilers for these devices. And
Okay.
the main reason for that is because those compilers are different from using classical
Yeah,
devices.
exactly.
So we at 1QBit and other parties, of course, are also creating these. So what we are doing is we are taking the complexity away of the hardware from the end user, and the
Yeah.
end user being a generic software developer who's been trained to work on classical devices, been trained on certain languages, so that they don't all have to learn what the hardware does,
Yeah.
how do we interact with it, and they don't need to learn a new language. So the Azure service that I was talking about,
Yeah.
it would have a Python interface, for example.
Okay.
Um, one of the other language that it will support is I think C Sharp.
Okay.
So basically the languages that people are already conversant with, those are the languages they'll be using. Nothing special. There would be documentation, of course, which would tell people that whether it's okay for you to assume similar resourcing and similar APIs like the other Azure services, or would the API look a bit different?
Okay.
So it's possible it'll look a bit different just because of the specific nature of the problems that Quantum Azure would be targeting. But on a high level, nobody would need to learn new languages. Nobody would need to learn the basics to be able to use these resources.
Okay. 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 So yeah, that's something good for developers, I guess. That's not a
Yeah.
complex path to develop something on quantum computing. Yeah. Uh,
Yes.
so moving forward, can you tell me something about like what one qubit actually does? Like you just listed some of the tasks already, but what is the main focus of one qubit? Like, are they building quantum computers, or they're just the software providers? Yeah.
Yeah. So we are not the hardware manufacturer.
Okay.
We don't build any chips. We've never built any chip. We are just the software provider. So the first thing is the low-level compilers. So
Yeah.
we build those low-level compilers because within quantum computing there are different paradigms.
Yeah.
Two of the most famous ones and prevalent ones are quantum annealing and quantum gate model.
Yeah.
Both of them work differently. Both of them focus on different kinds of problems, and both of them require different compilers to be
Okay.
able to access them
Okay.
and make wrappers around them. So we work with both. We provide compilers for both, but our main focus is to help industry partners
Okay.
connect with quantum computing. So a lot of our work is done in understanding different hard problems that different industry verticals face, and
Okay.
then transforming those problems to be able to then use our compilers to put on devices to test those.
Okay.
Um, that is the major part. Now, quantum computing or quantum computer is a tool. It's
Yeah.
not a solution. It's a tool that uses or helps you to solve a problem. So
Mm-hmm.
in the end, when the goal is to actually solve a client's problem, many a times it is solved using a hybrid approach, where
Mm-hmm.
by hybrid I mean some kind of combination of quantum computing and classical computing.
Okay.
So to be able to design those things, to be able to efficiently code those things, to be able to provide products
Okay.
which actually perform, that is what one qubit does. Um,
Okay.
our main industry verticals are healthcare, finance, and material science. So those are the three main verticals that we focus on.
Yeah. Okay. Uh, so that was really nice. Pranavi, do you have any questions particularly for Jaspreet?
Oh yes, I've been hearing so out of all these things, basically I've been interested into quantum myself since a few months, I would say. So of all these words that I've come across, how would you say quantum computation is one thing. So there are so many others like QML and quantum annealing, the work that I saw, well, the paper you had. Of course, I did not really go through it or understand much, but could you tell us about all these things? And then there's post-quantum cryptography, there's quantum cryptography, and so many other things like quantum entanglement and all those words related to it. So if you were to draw a broad category in short,
Yeah,
maybe,
yeah,
so
yeah,
please.
yes. Yes, so probably what you're asking for is a high level glossary and bucketing these terms. Um, so on the top would be quantum computing. Then would be what are the two types of quantum computing? Uh, one would be quantum gate model computing. The other would be quantum
Okay.
annealing.
Okay.
Then would be what are the major applications or major areas of application that people are working on. That would be QML, which basically means quantum machine learning.
Okay.
That would be quantum cryptography, which basically means people trying to come up with novel algorithms using quantum computing to make secured ways uh, just to fool, just to fail proof their currently existing cryptography mechanisms.
Yes.
So quantum cryptography itself is a big field where you are using quantum computing to either come up with new algorithms or trying to break the current ones. Quantum machine learning, as I said, is the whole field of studying machine learning from the perspective of quantum computing. So what that means is looking at the classical algorithms of quantum or machine learning and trying to find ways to make them more efficient and effective by introducing quantum computing or quantum phenomena in it. The other terms that you used, which is quantum entanglement, quantum tunneling, um, these are the properties that people study or need to study to understand what quantum computing is. It has nothing to do with the applications, it has nothing to do with the algorithms, but at the basic level, if you want to understand quantum computing, you would go into the concepts of what quantum entanglement is, what quantum tunneling is, because it helps you understand why quantum computing is powerful. So that is the third bucket. Before I go further, was that almost clear? I know it's not possible to explain everything, but I just try to give you a high level overview.
Yes, no, of course it is. And since we were talking about quantum technology, so one of the very basic questions is when people compare classical technology and quantum technology. So it's mostly that we talk about the classical bit and the qubit. So if you were to somehow explain in short, why is it that we prefer quantum technology over these things? So how can we?
Yeah. So the naivest way of explaining, and I don't really like this way, but it's a way that most people would get it. It's not completely wrong as well, so it's okay. So the bits as we see today are 0 and 1, and what we mean by that is whether the transistor is on or off. And what we mean by that is if the current is below a certain threshold, we call it off, we call it a 0. If the current is above that threshold, we call it a 1, and we say it's on. So what that means is every information that we send or process in classical computing is using zeros and ones, and that is a big part of the digital courses that you've learned in your engineering. What that does is it actually restricts the way a problem is solved when you give that problem to a computer. So if it's an optimization problem, for example, where you've given it an equation where the variables in that equation can only take 0 and 1, and let's say it had 4 variables. So what classical computing needs to do is it needs to look at 4 variables and different combinations of it. And after it has tested all the combinations, it would give you an answer as to what combination, for example, maximizes or minimizes that function. So like when it scales, which is when we go from 4 to 10 variables, when we go from 10 to 100 variables, the enumerations that need to be done, all the possible combinations that need to be seen, they increase exponentially. So that's why for certain problems above a specific size, classical computers would take from hours to days to months to years to millions of years to solve that problem. And that's the basic principle of why our cryptography exists. So it's not that the cryptography we do today is fail proof. If we were given a million years, we would be able to crack it. But because nobody has that time, we say it is fail proof. Quantum, on the other hand, which is when we talk about qubits, it has the ability to have a same bit in different superposition states. So what that means is if you have 2 bits or if you have 4 bits, you would be able to look into 16 different combinations of those 4 bits without enumerating all of them individually. So that really brings down the amount of computation or the amount of time required to process a particular information. So that is the most high level, naive way of saying it. When you actually look into the courses, you would also start saying what I'm saying, that is not the scientific way of explaining it, but it's still not untrue, so it's okay.
Okay, so since we've been talking about QML previously, and since you've been working with it since long, so there are a few things related to QML that come up these days. Like there's a thing called first generation and second generation. And then there's a problem that people say that classical data, the main problem people face with QML is that the classical data cannot be applied to it. Or, I mean, if we were, suppose, given a cloud today, like we have talked about the Azure cloud, and if we were to supposedly perform a QML problem, then would we be able to use our classical data for it?
Yeah, good question. So yes, there are classical algorithms and classical data. Then there's quantum algorithms and quantum data. And then there's the combination of all of this. So the combination is you can have classical data and you can use quantum algorithms on it. That is true. You can do so. We've done
Okay.
that. You can have quantum data and you can have quantum algorithms on it. Nobody has been able to do that because there are restrictions, because quantum data can only exist in quantum RAMs.
Okay.
So that is a completely different area. That is a completely different area of research, completely different area of studies, and actually the area that we don't work in. Not that we don't have people who understand it, but we don't work in that area. There's no specific reason. Probably the only reason is that it is way into the future than the near term quantum applications that we as a business need to focus on. So if I was a researcher and if I was a professor in a university, I would probably focus on it because it is way more powerful than running quantum algorithms on classical data. It's way more powerful to run quantum algorithms on quantum data. But because one qubit is a business, because we need to realize profits and other things sooner, one qubit focuses on near term quantum computing. So right now the focus is, let's not change the data. Let's keep working on classical data. Let's apply quantum algorithms on it.
Okay.
Okay.
So you mentioned something about research, that research is very important in this field. So for research, I think students need to be mentored with the industry. It's not just the professors who are gonna help us, because they are not the actual ones who are going to work in the industry. So how is this student industry interaction present in quantum field? Like how one should other
It is
countries.
pretty. It is pretty good. Yeah, it is pretty good in places where. So let me put it this way: cities where there are universities which have quantum programs,
Yeah.
and cities where there are companies that work in quantum computing. This is prevalent pretty nicely and widely. Why I say that? Um, I think almost all of the managerial and top positions that people hold in one qubit are held by people who joined one qubit as interns
Okay.
back in 2013 and 2012 and 2014.
Okay.
What that means is there was this collaboration between the universities, the academia, and an industry that brought us all to one qubit. And that's how we stayed in one qubit and became something.
Yeah.
It is continuing now as well. Like we have a very strong internship program in one qubit where on average every semester we have around 10 to 12, if not more, interns
Okay.
that are at one time at one qubit.
Yeah.
Whether that happens everywhere, I think it happens in Microsoft. I think it happens in Google. I
Yeah.
think it happens in D-Wave. So I would say it does exist. Now the problem is there are not many companies who work in quantum computing. So
Exactly.
at a bigger scale, at the world level, um, there are not many opportunities. So the sad part is if somebody from India, for example, is interested and would like to spend their 6 months of internship, and I think your program has changed now, it might not be 6 months, they probably won't get a company in India who does it.
Yeah.
Whether they can somehow get engaged with Microsoft India and Amazon India and Google India to do this, probably yes. I don't know how Google India is connected to the quantum program based out of Santa Barbara, California, but they should be able to connect you. So my suggestion would be that students get together, bring this up with the placement coordinator that
Yeah.
you have, who
Okay.
brings it up with the Microsofts and the Amazons and the Googles, that our students are interested. Would they be willing to somehow connect them to the quantum programs that they
Yeah.
have based out of US, and thus arrange the internships? Because I think internships can exist via remote working.
Yeah.
You should be able to go to your Microsoft office in India and still be an intern who
Yeah.
probably has a supervisor in Seattle. So that shouldn't be a
Exactly.
problem.
Exactly. Yeah. So I guess that's really important for students to, like, this should not be a barrier, I guess. Uh, like working remotely or they not being able to go to foreign should not be something which should stop them from learning. That was the motive of bringing this
Yeah.
point up. Yeah.
Yes, of
Mhm.
course. And I so much hope that one qubit had more resources to open up an office in India, but currently we don't. Currently we have our 3 offices, but all of them are in Canada. But and we have people who work out of one office and have a mentor in the other office. So I
Okay.
think the only thing that's required is for Microsoft India or the Google India to understand that and basically provide their premises to be able to take this forward.
Yeah. Okay.
Something I would like to ask. Maybe I'm going back to the basics again. We went very deep. Something you mentioned with one qubit was that you are working in, I guess, health sector and 2 more sectors you mentioned. And as you also mentioned that as of now, the most powerful quantum computer is just 50 to 52 qubits, and it cannot actually solve some real world problems. So what is one qubit working on in these areas, like healthcare areas? Are you working on research or are you working on solving some issues?
Yeah, very good question. So our company is divided into certain divisions. Um, 2 of those divisions are completely focused on research within these industry verticals. Um, the other 2 divisions are working on solving the problems today using classical computing, but translating them into a form that when tomorrow the quantum computing scales up, they would just have to swap the solver and they won't have to change anything else. So
Okay.
we are currently solving their problem using classical computers. So they are getting the value out of it, but they have also proved their systems to quantum disruption.
Okay.
That's a great insight.
Yeah. Exactly. Um,
Well, so since we were talking about students and quantum technology, quantum applications, so if we could somehow relate open source with it, do you think like people like us, students like us, developers like us, could somehow um, contribute towards this? Or and if we can, then what could be the application then
Yeah,
we could work on?
yeah. Um, I would encourage you to search for Penny Lane. I think it's Penny Lane, PENNYLANE. I think it's an open source library for quantum machine learning. And there are similar libraries coming up for other quantum algorithms. I think eventually it has to be an open source model. Um, for example, we have certain patents, other companies have certain patents. Uh, of course, there's value in patents, but if the industry has to evolve, if it has to be widespread enough to to gain more interest and get more people interested, especially at the student level, for them to be interested enough to take it up as masters and PhDs, to actually develop and advance this more. Open source is the way to go about it. Whether you would find it easy or hard to contribute today, I would say hard, because of course, the complexities involved, but that's the way to start. Slowly getting to the links within that library, reading more about things, taking few courses would eventually be the way to go about it until, as I mentioned in the beginning, until there are actually courses that are rolled out in universities like Thapar, and people actually get basics and are tested on those basics and get grades. Until that point, you'll have to depend on such exercises. Yeah.
So Thapar, I guess, launched nano computing and quantum computing elective for us this year. So I
Nice.
guess it's moving forward.
That's awesome. Who,
Yeah,
if I might ask, who's the? Do you know who's running that program? Which department would that be in?
that's I guess under computer science. Uh, that is actually they in this year they have outsourced this program to industry as well. Like they have machine learning program and DevOps program being outsourced to startups from various parts of the world. So like we have machine learning
Nice,
being done by
nice,
Virginia Tech. So yeah, so actually they are expanding their wings and providing way more options to
awesome,
students. Okay, so I
nice.
just remembered something, and it's for sake of our audience. I saw a video on quantum computing by Siraj. I hope most of them know. If not, you can search it on YouTube. It's Siraj Raval, and he was using something which was not the quantum computing actually, but it was like simulating quantum computing. So he was using some library kind of thing, which was writing quantum algorithms and using it to simulate the quantum computing. So how do you think that uh, these tools gonna help these students? Like they don't have actual environment, but they can simulate it.
Yeah,
How do they
so it's
compare to
really,
the actual
yeah,
computer?
yeah. It's actually a very good way of, I would say, very good way of testing things. We ourselves have simulated algorithms for different kinds of computings. Um, Good thing to test, good way to learn, um, easily available. We of course use the simulated algorithms as well. They're good for testing. They are good for easy access to people without the actual hardware. The only restriction is because it's simulating quantum phenomena, and if simulating it was so easier, then we would never need quantum phenomena. So it's very restrictive in size, of course, even more restrictive than what the quantum itself is today. So, but again, for testing your algorithms, for developing algorithms on smaller toy cases, it's a good thing.
Okay. Okay, so I guess you have limited time and you need to go back to work. So I'll allow you and thank you for joining us. Like it's really, really good experience to, having a talk with someone from quantum computing and like it's really awesome. Uh, Shubhangriya, can you just say a few words for Jaspreet and bid him well?
Yeah. Thank you so much, Jaspreet sir, for having your time. You're saving your precious time for us, and it's good to see. It's good to interact with an alumni of a college, and I hope that this podcast itself creates a sort of inspiration for a lot of people who are most of the times usually bamboozled by the world of quantum computing. And I just hope that this must be having an informative session. And yeah, I just hope that a lot of people like do take interest and start to like study and maybe like research about more. So once again,
Yeah.
sir, thank you so much for being there on the podcast, and it's an honor. It's really an honor to have you with us.
Oh, no, no worries at all. I really enjoyed it, and thanks for asking me about it. And also, I want to congratulate you guys for taking up this initiative. I think back in time, we did not do it. Now, if I want to go back, I would do it. So I want to congratulate you guys for doing this and
Thank you,
doing
sir.
this for bringing in different people who worked in different industries and from Thapar. So I'm sure somebody would be looking forward to hear on some particular technology or some particular work area where somebody else has worked in and excelled. So good luck to you all, and thank you again.
Thank you so
Okay.
much, sir.
Bye.
So that was Jaspreet. for an episode of Raw Talent. Stay tuned, guys, for more exciting podcasts like this. Thank you.